Hi everybody, this is Dr. Bricker here with a review for the final exam. So the final exam is Wednesday, May 5th from 5 to 7 in class. Now the exam is going to be between 20 and 22 questions, so at most there's probably 2 questions per chapter. So 1 to 2. It's over the entire semester, so it's sort of a wide kind of test, but not a very deep kind of test. So, the basic ideas. We've covered a lot of material, though that's what makes it difficult. So 20 to 22 questions, multiple choice, but you have to show your work like usual. There actually are going to be an additional 1 to 2 bonus questions from Chapter 29. So Chapter 29, completely bonus material. If you don't want to do Chapter 29, you don't have to worry about it. As far as studying for the test, definitely go back through the practice exams. You know where those are on Brightspace. Go back through the actual exams. Now you remember the first exam was online, so you'll have to go to Brightspace, click on quizzes, it's actually called, and you'll see exam 1 there, and you can go through and take a look at that. The other two, exam 2 and exam 3, were actually in-person tests. So most everybody's got their exam 2 back. The exam 3 I'm giving back actually today in class. I'm making this video on Monday of dead week. Anyway, doesn't matter. So review the practice tests, the actual tests, go back through the homework. I think by the time the final comes around, you would have seen all of the questions on the final in one form or another, either on the practice tests, the actual tests, homework, other examples from the PowerPoint. So yeah, take a look back at the PowerPoints. Review the chapters. If you can't read all the chapters, you don't have time to go back through all the chapters. At least go to the ends of the chapters and look at the reviews and the summaries. They're pretty good there. Now, as far as the test goes, you are allowed 2 pages of notes this time. So 2 8.5 by 11 sheets of paper, both sides. Put whatever you want on there. Okay? Good. So let's take a look at the actual material for the test. Okay, it all started on a cold day in January when we started with Chapter 20, which is called Electric Fields and Electric Forces. So the first thing we did was to figure out what the fundamental charge is. So 1.6 to the minus 19th coulombs. So if it's a proton, it has plus 1.6 to the minus 19. If it's an electron, it has minus 1.6 to the minus 19th. So positive charges, we saw that electric fields go away everywhere. Negative charges, electric fields go towards. The first lab we did, we looked at the idea that there's positive and negative charges. So this represents electric field going away from positive towards negative charges. We looked at the force between charges. So K, Q1, Q2, distance between those charges squared. So opposites attract, like charges repel. I'm sure you'll see some kind of problem involving Coulomb's law. K is a constant, 9 times 10 to the 9th newtons meters squared per coulomb squared. I'll give you the constants. You don't have to write those things down. So the idea is if you have a charge here and a charge here, these are just like charges. This is the distance between them. These actually repel each other. And here's the formula for it. So absolute value on the charges. This doesn't tell you the direction of the charges. You just have to know that if it's a positive charge versus a positive charge, those are like charges, they repel. If these were both negatives, they would also repel. If one was positive and one was negative, they'd actually would attract. Okay, so you'll probably see something with that. We also looked at the electric field associated with a point charge. So for a point charge, that's just a single charge, the electric field K, Q over R squared. So if you have a charge, it has an electric field. Here's the formula for it. Again, it's away from positive charges and towards negative charges. We also looked at the electric field due to a capacitor. So it seems like a long time since we've done capacitors, but here's a capacitor. One plate is positively charged, one plate is negatively charged. The electric field goes from the positive side to the negative side. This is plus Q, this is minus Q. The capital Q's and just mean a collection of charges. So the electric field due to this arrangement was Q, A, and then epsilon naught here. And epsilon naught was just another constant that we had. 8.85 to the minus 12th coulomb squared per Newton meter squared. And again, I would give you the constants. So we had the electric field due to a point charge. We had the electric field due to a capacitor. Here's the magnitude of the electric field. Sometimes this is written as sigma over epsilon naught. And sigma is the charge per area. Now it's worth noting that this Q is just the charge on one of the plates. You don't add these together or anything like that. And the area is just the area of one of the plates. We did square plates, circular plates. It's just the area of a plate. Now what can you use the electric field for? It's to figure out the force on a charge. So if you knew what the electric field strength was, and you put a charge in the electric field, it's going to experience a force. So this part looks just like m times g, right? This is from Physics 220. The force would be mass times the gravitational field. Here, the force is the charge times the electric field. I just wrote this so you can see the analogy between those. We did problems like we had a charge, like a string that was charged, an electric field, what's the tension in the string, that sort of thing. So again, look back at the first test, first practice test, and also the homework that goes along with that. You'll see a lot of different problems involving this idea. So this is really chapter 20, all the information from chapter 20. So you'll see probably at least 2 problems from chapter 20. Chapter 20 was actually a pretty large chapter. Okay, then we moved on to chapter 21. Okay, so chapter 21, electrical potential. So potential, again, means voltage. So we ended up doing circuits later on, but here we were just looking at it at electrical potential, or in other words, voltage, really on the atomic scale, really small, and then we expanded that to look at actual circuits. So the first place we saw this was when we looked at electrical potential energy. So this is electrical potential energy. This is equal to Q times electrical potential. It's confusing because they sound similar, but they're not the same thing, but they are related to each other. So this is energy. This is electrical potential. Electrical potential, or commonly called voltage. So this is measured in volts. This is measured in joules. I think it's helpful to remember that a volt is a joule per coulomb. So if this is joules per coulomb, you multiply it by how many coulombs you have. That will tell you the amount of energy. So if you knew the voltage at a certain region in space, and you want to try to put a charge there, you'll know how much potential energy is stored. And if you're storing electrical potential energy, then you must be doing some work to actually get the charge there. So going back to the example with the capacitor here. So the electric field, as you know, goes this way. This means higher voltage to lower voltage. So if you put a positive charge here, it wants to go downhill, right, from a higher potential to a lower potential. Okay, so that's the idea. Electrical potential difference. Sorry, I've got my window open today. A little breezy out. So this is the direction of the electric field. How it relates to electrical potential is we go from a higher electrical potential, or in other words, a higher voltage, to a lower voltage. So this positive charge would naturally want to go this direction. Now, the electrical world is a little more complicated than the world that we've seen, the macro world of Physics 220. If you put a negative charge here, a negative charge does the opposite. It wants to go uphill. You can kind of see it too by the fact that this is a negatively charged plate. If you place this charge here, it wants to go this way, the opposite direction of the electric field, whereas this positive charge likes to go with the direction of the electric field. Okay, so this positive charge would go this way. It would lose electrical potential energy as it speeds up to the other side. Okay, good. So one sort of problem we did here was to change electrical potential energy into kinetic energy. This is really a physics 220 idea, this idea, but in terms of electricity, the change in electrical potential energy I could write in terms of voltage. Oops, there's actually a minus there. Make a note of that. Change in potential energy is equal to minus the change in kinetic energy. Then I could replace delta U with Q times delta V. Same thing, minus the change in kinetic energy. So we did problems like you take an electron, you put it in a potential difference scenario, and you see how fast it's going afterwards. So I'm sure you'll see something like that. I could expand this a little bit. Q delta V minus 1/2 mv final squared. Be careful, this is velocity, this is voltage, minus 1/2 mv initial squared. So hopefully you remember those. We accelerated particles through potential differences and figured out how fast they were going afterwards. So make sure that you take a look back at this idea. You'll see some kind of a question on the test about that. I could expand this a little bit more if I wanted to. QV final minus QV initial. That's the change in potential. So if I distribute this minus sign through, I would have 1/2 mv initial squared minus 1/2 mv final squared. So these statements are all equivalent to each other. Okay, good. And going back to the capacitor example, you saw that if you go in the direction of the electric field, that's where the electrical potential is going from higher to lower. We actually came up with the formula for it. So the voltage across the capacitor is equal to E times D. And then D is the plate separation, the distance between the plates. So potential difference across a capacitor is equal to the electric field strength. This is the electric field strength. And then D is the plate separation. So another way of writing electric field when you're talking about a capacitor, voltage across the capacitor divided by the plate separation. This turns out to be volts per meter. We saw if you have a volt per meter, it's the same thing as a Newton per Coulomb. Okay? So that can be helpful. Sometimes you see electric field in newtons per coulomb, sometimes you see it in volts per meter. They're equivalent to each other. So a volt is a joule per coulomb. You can work out the units and see that it's the same as a Newton per Coulomb. So if you do have a couple of point charges, here's a Q1 and a Q2, and you want to figure out the energy between them. So you can bring Q1 here all on its own. If there's nothing else around, you can easily do that. Now when you try to bring Q2 here, Q1 is in the region, so either if they're the same charge, you have to do some work to put Q2 here. So let's just pick a scenario. This one's positively charged, this one's positively charged. So to put this one here by itself, you could easily do that. Right? There's nothing around it. Now when you try to bring Q2 here, Q2 is in the neighborhood of Q1, but they're both positively charged, so you have to do some work to do that. There's an amount of energy between these two, if you remember. This is K, whoops, no absolute value. Let me start over. K, Q1, Q2, and then the distance between those two, not squared. So if you have a Q1 here, you try to bring Q2 in, you're going to store some energy between these two. So that's the energy stored between charges. Now if Q2 were negative, this energy would turn out to be negative. Bringing Q2 here, if it's negative and Q1 is positive, you don't actually have to do any work. Q2 would like to be there. Now if you have several different charges, you'd have to add those all up. So if you try to bring a Q3 in and you want to figure out the energy between them, you'd have to add that to the whole mix. And going back to this idea of voltage, there's voltage between charges as well. You'd have to add up the total voltage. The nice thing about voltage is when you add them all up at a certain spot, they're just numbers. So this is what I'm trying to say. The total voltage in a certain spot, you just add them all up. So I guess I'll write it like this. K Q divided by R. This just means the first one, the second one, so 1 to however many you have. This is a fancy way of just saying you have to add up the total voltages. So if you remember, we did a problem like this. This could be Q1, Q2, Q3, and we want to figure out the voltage over here on this part. Maybe this is a triangle. So you have to figure out, or not a triangle, a square. You've got to figure out the voltage here because of this one, the voltage here because of this one, the voltage here because of this one. So then you would just add them all together. And R in the formula is the distance away. So this would be like R2. This one would be R3. This one would be R1. So you just add them all together to get the voltage. That's a little bit different than the electric field, if you remember. The electric field is a vector. So if you wanted to figure out the electric field at this spot, it's a lot more complicated. Let me just refresh your memory about that. So if you wanted to figure out the electric field here, and you had, let's just pretend these are all positive, Q1, Q2, and Q3, and you wanted to figure out the electric field here, because of Q1, the electric field is this way, because of Q3, the electric field is this way, because of Q2, the electric field is that way. So this is from the first one, this is this one, this is this one. This is a really complicated problem. You wouldn't see anything as tough as this on the test, trying to figure out the net electric field. But just remember, voltage is a lot easier because it's just a number. You just figure out the number here. The electric field you would have to take into account direction. So you wouldn't see anything as complicated as this, but you might see something like this. And if you go back through the practice test and the actual test, you'll see that. What if you had a positive charge here and a negative charge here, and you want to figure out the net electric field between those? Hopefully this is ringing a bell. You have to look at the direction. So let me pretend this is Q1, this is Q2, and you want to figure out the electric field here. So the electric field because of Q1 is this way, because it's away from a positive charge. The electric field at this spot because of Q2, negative charge, it's this way. So here's where you actually would just add them together. So hopefully that rings a bell as well. So the first test dealt with this whole idea of electric field, electric force, potential, that sort of thing. So when you look back through it, the first test was just over Chapter 20 and Chapter 21. Now, I didn't put anything on the final, or I'm not going to, about the electric field due to like a solid sphere or anything like that. Pretty much just sticking with either capacitors or individual point charges. And then the final thing in Chapter 21 was looking at capacitors in a little more detail. So with a capacitor, you put more charge on, a capacitor, you build up the electric field, you build up the potential difference across the capacitor. So we have this formula, Q is equal to C times delta V across the capacitor. This is how much charge you have. This is the voltage, and they're proportional to each other. And the constant that relates those together is something called capacitance. So now be careful, because charge is measured in coulombs. This is capacitance, which is measured in farads. So a farad is a coulomb per volt. I'm afraid to even write it because capacitance is a C. The units are farads, which are C over V. So just distinguish between the variable and the unit. So farads, that's what capacitance is measured in. So the more charge you put on, the more the voltage. The quantity that relates those together is called capacitance. And we saw that the capacitance is just depends on the actual physical situation you have of the area of the plates, the plate separation. Okay, so we have a formula for that, and it is for a parallel plate capacitor, capacitance was epsilon naught A over D. Okay, so I said it just depended on the physical parameters. By that I mean the area of the plate and the plate separation. This is just the area of one of the plates. Little d here is the distance between the plates. Okay, so we have this for the capacitance of a parallel plate capacitor. This is just in general true. This is the charge on a capacitor is proportional to the voltage, and that's the constant that regulates those together. We also saw the electric field because of a parallel plate capacitor, Q A epsilon naught. And then I guess the last thing I could put here, the voltage across the capacitor is E times D. So all these formulas work with each other as far as a capacitor goes. So on your formula sheet you can have a little capacitor section. And again, they all relate together. I didn't put energy of a capacitor on the final, so you don't have to worry about the energy that you store in a capacitor. Okay? And then we started to look at things in a more macroscopic way, more tangible way, with chapter 22, which is called current and resistance. So the amount of current that you have is equal to the amount of charge that crosses through some cross-sectional area in a certain amount of time. So the amount of current, how many coulombs per second you have, and a coulomb per second is an amp. So whenever you see amp, remember it actually means something, how many coulombs per second. And we're dealing with conventional current. I mean, in real life, the charge carriers are electrons in metal. Electrons are actually moving through metal. The conventional current, we just pretend that it's positive charges moving. So the question is, well, how do we get these charges to move? And the idea is you have a battery. What does the battery give you? Well, it gives you a potential difference. So with the battery, you have a separation of charge through chemical means, and then you provide a path for charges to actually leave. So for example, this is the positive side, this is the negative side. Let me put a switch here for a second. So the switch is open. Positive charges don't have anywhere to go. Negative charges don't have anywhere to go. But then when you close the switch, now you have a place for these to actually go. And that's where you can actually get current to flow. So the amount of current that you have flowing is proportional to the voltage here. So say a positive charge leaves, goes around, comes to the negative side. What the battery does then is take the positive charge that was over here and move it back to this plate, and then the whole thing goes back through. We talked about this in terms of a ski lift. So you're here at the top of a hill. You go down the hill, you're at the bottom. The ski lift, that's the battery in this analogy, lifts you back up to the top, and then you're free to go back through the whole circuit again. So the amount of current that you have is proportional to the voltage that you have here with the battery. So this is where we first saw Ohm's law. So V is equal to IR. So chapter 22, we just started talking about circuits, and then chapter 3, we did a lot more with circuit analysis. If you remember the lab that we did, we actually graphed, this is V and I, and then the slope here was the resistance. So the slope of this graph was the resistance. And you can see it from here too. This is equal to like y is equal to mx plus b. So if I've got current here on the horizontal axis, that represents x in this analogy. So the slope is the resistance. Okay, good. So with circuits, usually we assume that there's no resistance in the wires. In real life, there is. So resistance, it depends on what the wire is made out of. So this is resistivity, the length of the wire, and the cross-sectional area. So if this is a wire that has some length, the longer the wire is, the bigger the resistance. The thinner the wire, so the smaller the cross-sectional area, this is the area, pi r squared for a typical wire, round wire, and rho is the resistivity, and it's measured in ohms times meters, and depending on what it's made out of, the value of the resistivity changes. So if it's copper versus aluminum versus gold, these all have a different resistivity. So the resistivity is whatever it is. The resistance depends on the length and the cross-sectional area and what it's made out of. Okay, so unless they tell you otherwise, we assume there's no resistance in the wires, or anyway, it's really small compared to everything else. But if you want to take it into account, this is the formula that does so. The last thing really from chapter 22 is looking at the power that we have in a circuit, and we saw that it's I times V. Now I can also use this in conjunction with Ohm's law and write this in several different ways. So here's Ohm's law. I can take this and write this in a lot of different ways. So if I want to take like V and get rid of it, I can plug this in for V and get I squared times R. Or here, if I want to eliminate I solve for I in this formula and plug it in and get V squared over R. So these are all different ways of writing power. You've seen these before. Okay, either the power delivered by the battery. So the power delivered by the battery would be the current times the voltage. So if it's a battery, we usually write it like this, EMF. That just means voltage of the battery. So the power delivered by the battery is the current and the voltage. The power dissipated in the resistor would be I squared times R, or V squared over R. Or you could, if you know the voltage across the resistor, multiply it by the current. Okay? Good. The next chapter, chapter 23, we looked at circuits in more detail. So first thing we saw with chapter 23 was, let me write it here, chapter 23, just called circuits actually. So we had the junction rule. So these are different rules to help us solve some circuit problems. So if we have current going into a junction, like say, here's a current going into a junction. So if this is 5 amps going this way, this one's got to be, if this is 3, then you know that this one's got to be 2. Whatever goes in, 5 amps is going in. You don't lose any. 3 goes this way and 2 goes that way. So a nice analogy is to think about this as a river flowing. Okay, so then we saw series circuits and parallel circuits. So a series circuit, these resistors go one right after the next. And you don't have to have 3, you could have however many you have. So current's going to go this way. This is R1, R2, and R3. So in series, it's the same current that goes through the resistors, and then the total resistance adds up. So R1 plus R2 plus R3. Now the voltage of the battery, this would be V1 plus V2 plus V3, but the current is the same. Whoops. Current is same, right? It doesn't have anywhere to go, but same current goes through each of these. So voltages all add up, current is the same. In parallel, it's just the opposite. So this could be a parallel circuit. I'll write it like this so it really looks like they're all parallel. So here's the voltage of the battery. Now in parallel, the voltages are the same. So this is purely parallel. Current comes out, splits off. This is R1, R2, and R3. This would be I1, I2, and I3. It's the current that adds up. So if this is the total current is I1 plus I2 plus I3. But the voltages are the same. So if this is, say, 100 volts, these are all in parallel. This is 100, this is 100, this is 100. So the voltages are all the same. Meaning this would be V1 equal to V2 equal to V3. And the equivalent the equivalent resistance in this circuit, this is how I usually write it, 1 over R1 plus 1 over R2 plus 1 over R3. And if you have a common denominator way of doing it, add it up, flip it back over, or if you prefer to do it on your calculator, this is the same exact thing. Whoops. And then, raise that to the -1 power. So, keep that in mind, what each type of circuit, series and parallel, means. And I'm sure you'll see, some kind of combination of problems on that. Now, sometimes you have a circuit that's a combination of both sorts of scenarios, a more complex circuit, something like this. So if this is the voltage of the battery, this is R1, R2, R3. Here current goes this way. This is the total current from the battery. Some of it goes this way. Some of it goes this way. Now this is a combination of series and parallel. R2 and R3 are in parallel. Current comes in here, splits off. Some goes this way, some goes this way, then it comes back together. So R2 and R3 are in parallel, and this combination is in series with R1. So look back at exam 2. There was a problem just like this actually on exam 2, or practice exam 2. The way that we did this was to take this complex circuit, R2 and R3, combine R2 and R3 into one resistor, and then R2 and R3 combination is in series with R1, and you can turn that into a simple circuit, which just means one battery and one resistor. You can figure out the total current that way, and solve the problem that way. So look back at that circuit analysis idea. Man, a lot of this stuff seems so long ago, but really this was maybe a month and a couple of weeks ago, maybe 5 weeks or 6 weeks ago. Okay, so you'll definitely see a more complex circuit like this as well. Okay. Also in 23 we looked at RC circuits, which are resistors and capacitors in the same circuit. But I won't put that on the final. There's no RC circuit type questions on the final, and I didn't put like equivalent capacitance on the final either, so that'll save you a little bit of time. So no RC circuits and no capacitors in series and parallel. Okay, good. So that's chapter 22 and 23 are both about circuit analysis. Also on this second exam was magnetism. So that's chapter 24, magnetism. And there's two sides to that. There's what happens to a charge in a magnetic field, and then the other part is producing magnetic fields. So I guess the first thing we looked at was a bar magnet, actually, which has a north side and a south side. These always come together. You can't just have a north pole or a south pole. You always have dipoles, which means north and south side. So magnetic field lines leave the north side and go into the south side. We did the lab on that, if you remember. We looked at with a compass around, plotted out the magnetic field due to a bar magnet. So if you cut this in half, you get two small magnets. You never get just a north and a south side. So we have 3 different scenarios where we could actually calculate the magnetic field for different situations. The first one we looked at was a long straight wire. So if current is flowing this way, the magnetic field U0I over 2 pi r. So I is the current flowing, r is the distance from the wire to the point that we're talking about. Hopefully that looks okay. Yeah. So this is where we saw the first right-hand rule. So if current is flowing this direction, everywhere up here it's out at you, the magnetic field. Everywhere here it's into the page, right? Because the magnetic field, I don't know how this is going to look on this screen, but put your thumb in the direction of the current, and then the magnetic field lines loop around. So above the wire, they're out at you. Here, they're going back into the page. And here's the formula to predict how much this is, how much the magnetic field is. So if you have a couple of wires next to each other, you have to take that into account. So if you had another wire, maybe down here, I'll just call this one I1. You have another wire down here. This one I'll just say is I2. I2's magnetic field up here is into the page. and over here would be out of the page. So if you have to figure out the magnetic field between those, the first thing to do is to figure out which direction is the magnetic field because of I1, which is the direction of the magnetic field because of I2, and then you can see if you have to add them together. Same direction means you add them together. So you can do something like that. So again, look back at the practice test, the actual test, homework questions. That's the best way to approach this this final, in my opinion. Another scenario we had was at the center of a loop. So if you have current flowing this direction, we could figure out the magnetic field right in the center. Here it's actually put your thumb in the direction of the current. The magnetic field is out at you in the center here. So here it's actually out at you. The strength of it, a little windy again, mu 0 I over 2 R. R is the actual size of this. And I is the amount of current flowing. Now if current were going the other direction, if current were going that way, maybe I'll make this one green. Inside the loop, if my thumb is the direction of the current, magnetic field would be into the page there. The final scenario we had was a solenoid. So mu 0 I times the turns ratio. So N is the number of turns, and then L is the length. Sometimes the turns and the length are given independently. Sometimes they're actually given as just one unit, like the turns per length ratio. So that's a loop. This is for a solenoid. Okay, so make sure that you have those three situations. Maybe a picture would be helpful. Here's a solenoid. Something like this. This might be a better way of drawing it. So this is a whole bunch of loops spread out. This is the length of it. Note that this does not depend on the cross-sectional area here. It's just the length and the amount of turns. And this is the magnetic field at the center of the solenoid. This makes up an MRI machine. Okay, so those are the three situations that we had to produce a magnetic field. Now what if you have a charge moving in some external magnetic field? It experiences a force. So Q, VB, sine of, I'll just call it theta. So this is the second right-hand rule where you have to line these things up. For example, if V is this way, B is this way, the force would actually be out at you. So V, B, force is out of the page. That's on a positive charge. So that means out at you. Force would be out at you. If this is a positive charge, moving to the right, magnetic field's up. You know, line those things up. V, that's where your thumb was. B, your pointer finger, and then the force, your other fingers coming out at you. So this is the magnitude of the force. This is the charge, VB, and then this is the angle between V and B. Here it just so happens to be 90 degrees, and the sine of 90 would be 1. Okay, so we did a lot with this. We looked at things moving in a circle, like on the second test, we had the mass spectrometer problem. So this force can make things move in a circle. So take a look back at the mass spec problems that we did. A spectrometer. Hopefully I spelled that right. This was on the second test, and we did some homework questions on it as well. So you'll see something with, I'm sure, using this force law. I mean, I'd have to give you everything except for one of these, and then you'd have to figure out the other one. Here's an application, though, that was really neat that we looked at, mass spectrometers. And then a little bit of Chapter 25 actually made its way into the second test. So Chapter 25 is called Induction and E&M Waves. Induction and EM waves. So induction, that's Faraday's law. A changing magnetic field produces an electric field. Going along with that is Lenz's law. Lenz's law is the part that made it onto the second test. So if you have a loop here, and say I've got a magnetic field going through it. Maybe the magnetic field is this way. This could be like a bar magnet, north side facing down. The magnetic field lines would be going through it. What if I move the magnet closer? Now I've got more magnetic field lines going through it because the bar magnet's closer. So we did this like initial, and this is final. Which way is the induced current? That's what Lenz's law is for. L-E-N-Z. Which way is the induced current? Well, nature was in this situation. It wants to stay in that situation, only having 4. And here I've got 6. So the induced current is going to flow in such a way to try to kill off this increase. So the induced current is actually going to flow this way, and then inside the loop, the magnetic field associated with this green would be this way, trying to kill off the increase. So take a look back at Lenz's law. You'll definitely see a Lenz's law problem on the test. Okay, so the second test dealt with chapter 22, 23, and just the very beginning of 24, which was on, 22, 23, 24. Let me write this down. Exam 2 was 22 through 24, and just a little bit of 25, which is the Lenz's law part. So exam 1 was just 20 and 21. Okay? Very good. And then moving into the third exam, we did Faraday's law. Changing magnetic flux produces an electric field. The way we did it, we wrote it in terms of induced voltage and magnetic flux. Okay, there's a minus sign technically here, just meaning it goes along with Lenz's law. The induced current tries to get us back to where we started. Okay, so here N is the number of loops you have, turns, loops, whatever you want to call it. Magnetic flux is magnetic field strength, area, and then the angle between B and A. So for example, if this is a loop, this is the area vector perpendicular to the loop. So if there's a magnetic field going through here this way, this is the case where they're actually lined up with each other. So theta would be 0 here. So something has to change. Either the magnetic field strength has to change, the area has to change, or the angle between those has to change. You can change the angle between here pretty easily if you just rotate the loop. If you rotate the loop, the area vector and B change. That's the idea behind a generator. So you get something to turn this loop for you, like some kind of waterfall or something like that. You get this to rotate, you can generate electricity that way. Okay? Changing the area of the loop is harder. You can do it though. Take the loop and actually scrunch it up or stretch it out. You can change the area. Practically speaking, that's not really done. And you can change the magnetic field strength. So on the third test, we had a problem where the magnetic field strength went from something to nothing in a certain amount of time, and you could produce some electricity that way. Now Ohm's law still works with this. You know, V is equal to IR. Here the V is the EMF. So this still works. There's no reason that wouldn't. Okay, good. So in a way, chapter 25 is kind of a transitional chapter. So we see that a changing magnetic field produces an electric field, and we also saw that a changing electric field then produces a magnetic field, and that's the basis for an electromagnetic wave. So somehow you have a situation like this. Maybe this is positively charged and this is negatively charged, hooked up to a battery somehow. If you could flip this around, this is positive and this is negative. Somehow you flip this around, you make this positive and this negative. Now you have a changing electric field, right? The electric field was going this way. Now the electric field is going this way. Changing electric field. That produces a magnetic field. So magnetic field went from nothing to something. So that produces a magnetic field, and so on and so on. That's what an electromagnetic wave is. So first you have to produce the changing electric field, or changing magnetic field, and then that produces its counterpart, and that travels through space. So if you're over here and you're observing this, the information doesn't reach you instantly, right? So there's an electric field, it changes. How do you know it changes? Well, that information has to travel to you. That's what an electromagnetic wave is, that information getting to you. So we saw some properties of electromagnetic waves. First of all, they all travel at the speed of light, whether it's visible light, gamma radiation, radio waves, whatever it is, they all travel at the speed of light. The electric field part and magnetic field part have the same energy, but their amplitudes are related like this. The electric field part is equal to the speed of light times the magnetic field part. This makes it look like the magnetic field part is a lot less because you have to multiply it by the speed of light. It's just that the units we've chosen make it so. We also looked at intensity, power of a wave, how the electric field part is related to the energy, and so on. But I think as far as electromagnetic waves go, I mean, this is a good part to know. I didn't put anything with power and intensity on the third test, so I won't put it on the final either. It is in chapter 25, though. So this is looking at the wave behavior. Also in chapter 25 is the first time we saw light behaving as a particle, like a photon. I didn't talk about it at that time, though. It's not till we went into chapter 28 that I started talking about light as a photon yet. First time, when you're looking through the notes, though, you'll see this in chapter 25. Energy is equal to h times F. But in chapter 25, I didn't really mention it. Again, I didn't talk about this until we went into chapter 28. Okay, good. So the third test, this is where we first saw Faraday's law, a little bit of properties with electromagnetic waves, and then we went into geometric optics and wave optics. So geometric optics, that's where we're looking at light as a behaving like a ray. So geometric optics. Okay, so exam 3 again. We finished up chapter 25. Then we went to chapter 18. Actually, the book calls it ray optics. This is lenses, not L-E-N-Z, L-E-N-S-E-S, and mirrors. So a lot of geometry involved in these kind of problems. So I guess the biggest thing to get out of this is a few things. We had Snell's law. We had the Snell's law activity, so look back at that. So Snell's law, N1 sine theta 1, N2 sine of theta 2. So this is when you go from one material to another material. N1 theta 1, light could bend. This is N2. This one is theta 2. So Snell's law governs this behavior. Here you can see that N2 has to be bigger than N1 because light is refracting. So this is light refracting this direction. So this is the first thing we saw with refraction. So refraction is the bending of light. I guess I should say, I didn't really say anything about reflection yet. Reflection is this. Light comes in, hits here, goes this way. So all these angles are measured from the normal. So this is the incident angle. This is the reflected angle. Those are actually equal to each other. So you could use geometry to solve a lot of these reflection problems. That's why I usually call it geometric optics, but ray optics is probably a better way of thinking about it. So usually we just think this is a ray going that way, this is a ray going this way. But really these things have their electric field part, their magnetic field part. It's just when we look at them in this kind of macroscopic way, the wave behavior is not coming out. This is the ray behavior being exposed. Okay, so I digressed a little bit. This is reflection. Snell's law is refraction. And then we had lenses and mirrors. So 1 over S plus 1 over S prime is 1 over F. This works for lenses and mirrors. So for lenses, we have a couple of different kinds. This is a converging, or sometimes called convex lens. This is a diverging or concave lens. So for this kind of a lens, S prime could be positive or negative. For this kind, S prime is only negative. Focal length here, this is positive. Focal length here, negative. For either case, S is positive. Remember, S is the object distance. This is the focal length. And this is the image distance. Whoops, sorry about that. I'm kind of running out of room here, but S prime being positive, this means real and inverted. This means virtual. If it's virtual, it's upright. It means the same thing over here. Diverging lenses, you only get virtual upright images. This is the only thing that you could get. So take a look back at the ray diagrams for that. Okay, the other thing, this is the lens maker's equation. Going along with that is this, H prime over H minus S prime over S. So if the magnification is positive, that means it's upright. And if the magnification is negative, this means inverted. Well, you know, if it's upright, it's got to be virtual, right? Upright and virtual always go together. And if it's inverted, inverted and real always go together. All right, good. So that's lenses. We did this more recently, so this is probably more familiar to you than looking at electric fields because of protons or something like that, because we just did this in the last couple of weeks or so as far as the test goes. It also, the lens maker's equation also works with mirrors. So we have this kind of a mirror, and we got this kind of a mirror. So there's the, this is the object. So regardless, object distance, this is always positive. Now S prime here could be positive or negative. S prime here can only be negative. So, this goes with this, this goes with this. F here is positive, F here is negative. So here, S prime being positive, same kind of idea that we had with the lens. S prime positive, this is a real inverted image. This is virtual and upright. So you can see this always only gives you negative. Virtual, upright. So in a sense, this convex mirror behaves like a diverging lens. Concave mirror. So a convex mirror behaves like a diverging lens, and a concave mirror behaves like a converging lens. Okay, lens maker's equation, also the same thing here, works for magnification. So really, if you have a lens or a mirror, you have this equation and this equation to work with. And these little tips here can really help you solve some problems. Like for example, on the third test, if you go back, one of the questions dealt with the magnification. I can't remember if it was for a convex mirror or a diverging lens. The magnification's got to be positive for that because you only have upright images, so you could have weeded it out right away. Only one of the answers had the magnification being positive, so immediately you could solve for that. So these little hints can help you solve some problems. Okay, then we went on to looking at, so this is looking at light as a ray, And then we went into looking at light as a wave. So wave optics. So chapter 17, wave optics. So take a look back at that chapter. There's a few different scenarios that we had when we looked at wave optics. We had double slit problems, single slit. So, look back through those. We also had diffraction gratings, which is really just a whole bunch of collection of slits. And then we had thin film interference. Thin films. So here, let me give you a hint for the final. I did not put a diffraction grating on there, but you'll have one of these, either a double slit or a single slit problem. Very straightforward one. Just know the differences between those. Double slit gives you where the bright spots are. Single slit where the dark spots are. So make sure that you have those straight. Build a little thing on your formula sheet. Double slit, do a picture, write the equations. Single slit, little picture, write down the equations, know what they mean. And then you'll definitely see a thin film problem again. So look back at the practice test and the actual test. Hopefully you have your little chart of what different things mean. Okay, so what I have here is from the third practice test. So when you do a thin film problem, the idea is light comes in here, and some of it's reflected from the first surface, goes through to the second material. So there's 3 layers, right? This usually is air, this is the film, this is the media that the film is deposited on. So some light is reflected here, some is refracted, and then some is reflected here. Here's your eye. Does this light and this light, do they arrive in phase? Now if they arrive in phase, they actually add together and you see them. Now if they arrive out of phase, they can kill each other off. That's anti-reflective coating. So out of phase means the wave looks like this from one side, from the other side, they kill each other off. Okay, so the first thing to do with this sort of question is to note, okay, air usually, this is the film, this is whatever it's deposited on. So you've got to determine if there's phase changes or not. So, look back through this. This is from the wave optics chapter. I made this chart before. You've seen this before. First thing, do we have constructive or destructive interference? Here, they tell you it's constructive. Oops, you can't see that. They tell you it's constructive in this practice test. On the actual third test, it was destructive. It was anti-reflective coating. Okay, so constructive versus destructive. We've got to know if there's 0 or 2 phase changes or 1 phase change. The way to do that is to look at the index of refraction of the film. Okay, so middle value, meaning it's greater than one of them, but it's less than the other. That's what we have in this practice test problem, right? This is 1, this is 1.25, this is 1.33. So this is the middle value, okay? Middle value for constructive interference, 2t is equal to m, wavelength in the film. For destructive interference, 2t would be m plus a half times wavelength in the film. Here it's constructive interference, we did this. Now on the actual test, it turned out to be the largest value. So on the actual test, this was the largest value. Okay, so largest value, we need to use this row. And it was destructive interference on the actual test. So largest value on the actual test, for destructive interference, it's this formula. Okay? So that's the way to proceed with this. Determine, first of all, do you have destructive or constructive, and then look at the relative indices of refraction. Middle value, use this information, constructive versus destructive. Largest or smallest value, okay, if it was the largest or smallest, you would use this. This is for constructive. This is for destructive. Okay? Good. So you'll definitely see a thin film problem on the test. Okay, and then, okay, so we looked at light as a ray. We looked at light behaving as a wave. We went on to chapter 28, which is light behaving kind of like as a particle, like a photon. So chapter 28 is when we transitioned into quantum physics. And the energy of a photon, h times f, hc over the wavelength. So this was alluded to a little bit in very end of chapter 25, but we really started talking about it here. So hc, this is our little trick we use, eV nanometers if you remember. So the energy that a photon has. Where we really paid a lot of attention to this, first of all, just thinking about it behaving like a photon, and then this behavior really comes out when we look at the photoelectric effect. So the maximum kinetic energy that an electron has. So the photoelectric effect is the idea you shine light on a piece of metal and you could liberate electrons. So the electrons grab onto this energy and they could leave the surface with a maximum kinetic energy that's determined by the energy, that the electrical energy that a photon has, minus something called the work function. Now when you did the most recent lab, the photoelectric effect, this is called the work function. This book uses E sub 0 for the work function. When you went through the lab, they use this as the work function. So if you're just trying to put everything together, usually this is the work function symbol, but here this book uses that. This energy that the photon has, I mean that's true, that's the energy it has, but usually we look at this like hc over the wavelength, or h times f, whatever you wanted to do. I'll just put same thing over here. Okay, same formula. Now if you want to completely stop the electron from moving, you can take the kinetic energy and turn it into electrical potential energy. So this would be the charge times the voltage, and it's an electron, and this is something called the stopping potential. So we could take this and put it into the formula here. E times V stop, this would be hc over the wavelength minus the work function. Or if you're doing it in terms of frequency, you can do it this way, hf minus the work function. Now if you're comfortable with electron volts, this is really helpful, because this would be, if you knew what the stopping potential was, say the stopping potential was 3.2, and we're talking about an electron, this energy would be 3.2 electron volts. Makes your life a lot easier. Now if you're not comfortable with electron volts, that's perfectly good. That's perfectly fine, I should say. You could do everything in joules, and then maybe you have to convert it back to electron volts. 1 electron volt, 1.6 to the minus 19th joules. Okay, so you'll definitely see some kind of photoelectric effect problem. This is Planck's constant. I would give that to you as well. So take a look back through the actual test, practice test, homework questions that we did. You can even take a look at the photoelectric effect lab that you've done recently. I mean, as far as labs go, you could even go back to the circuit FET, take a look at that. If you want to experiment with how different circuits go, I mean, you don't have to spend all day doing it, but you could look at series versus parallel circuits with the circuits FET that we did. You could also look back at the wave, wasn't really a lab, but I gave you some problems. So it was the wave behavior of light lab. So instead of doing an actual lab, there were some problems on mastering physics. Kind of like homework questions, just maybe a little bit more involved. So you have that to rely on too, in addition to just practice tests, this video, homework questions. You can take a look at the labs, especially the simulation ones, because you could really do it in real time. I guess the other thing about Chapter 28, we looked at the energy that a photon had. That's just for one photon. Now, if you want to, you could also, if one photon has that much energy, what if you have a whole collection of photons? And this was actually on the second test, or sorry, third test and third practice test. The power would be the total amount of energy divided by the amount of time. So if you know how much energy one photon has, multiply it by how many photons. Sorry, you can't see that. The power would be the energy that one of them has, multiplied it by the number of photons. divide it by the amount of time, and then you'll have the amount of energy. So this would be joules per second. So just be careful when you're doing these problems. Joule per second is a watt. Sometimes it's beneficial to look at electron volts. Sometimes, just be careful with the units. You might have to look at joules. This is again where we first started looking at transition of energy from lower energy levels to higher energy levels. That's an absorption of photon. So an electron can go up in energy if it absorbs a photon, go down in energy if it emits a photon. So also in chapter 28 we had those energy level and quantum jumps. So again, look at the practice test, third practice test, third actual test. The problem I'm thinking about is this was like 0 EV. I can't remember exactly what it was, but this was like, I'll just make up a problem. This is 4 EV, maybe this is 8 EV or something like that. So an electron could grab a 4 EV, go up to this energy level, or it could grab, if it's going from the ground state, all the way up to 8 EV, or if you're already in the second state, you can go up this direction. So you can make those transitions. You can't end up grabbing a 2.5 EV photon. That doesn't happen. You can only make these discrete jumps. And it works in reverse. So this is absorbing, this is emitting. You do the opposite. You do something like this. So the difference in energy between these different levels is hc over the wavelength, or h times f. Okay, so you saw one of those on the practice test, 3 on the actual test. So don't be surprised to see another problem that looks kind of like that. I didn't put anything about the uncertainty principle on it, and nothing like a particle in a well or anything like that. So that was the material that went through chapter 28. Now chapter 29, completely bonus material. I put that some videos on about chapter 29. There's a bonus homework set on chapter 29, atoms and molecules. So if you have time, take a look at that. Don't make that the focus of what you're doing, though. I think for chapter 29, maybe from section 29.1 up to 29.5, you'll see a lot of overlap in chapter 29 about why things happen in chemistry, actually. But bonus homework sets there. If you have time, take a look at chapter 29. I'll probably throw 1 or 2 5-point problems. I mean, there's going to be 20 problems, so maybe 1 or 2 problems from chapter 29 on, just as a bonus. So you're not required to do that. It's really neat stuff, but we've just kind of ran out of time to do all that. So if you have any questions, just email me. You have until Wednesday, really. Here's my email address one more time. gbricker@pnw.edu. So email me. We can talk about whatever you want. We can set up a WebEx meeting, kind of like an office hour. So we got about a week to go, a week and a day or so, getting towards the end. Hopefully everybody's staying safe, and hope to hear from you soon. Bye-bye.